Welcome back to our sessions on machine learning. We will be focusing on probabilistic graphical models. Today's session is focusing on kernels. If you have a recap about what we have done, we divide the whole series of sessions into 4 modules. In the first module, we focused on introduction to machine learning, probability and graphical models, where we covered what is machine learning, what is the significance of data in the machine learning framework, and what are the different focused areas of machine learning, etc. we covered. Also, since probability being a major requirement in the study of machine learning, we have revised the major component, major theory, major concepts required for machine learning as far as the probability is concerned. Also, we started with the directed graphical models, and also we looked at the mixture models and the expectation maximization algorithm. In today's session, we will be focusing on the second module, that is the kernels, Markov and hidden Markov models. And today's section exactly focusing on the first component of that is the kernels. Today's overview about the course is that we will be focusing on kernel function. Also, we looked at using kernel inside generalized linear models. We introduced the concept of kernel trick, and also we introduce what support vector machines. We move on to the first one, that is the kernel function. What is the kernel function is after all? We know that objects need to be represented before it is being used for some machine learning purposes. The objects can be of different nature, but if they are of fixed size, it will be easy to convert that into a machine friendly format by converting it to fixed size feature vectors. But many times all the objects may not be that friendly, in the sense that objects may not be of fixed length. There are many examples for objects being not having fixed length. First and foremost come to our mind maybe text documents. If you consider a number of text, each of the text may be of different length depending upon the number of words, sentences, page length, etc. That means the text documents are of different length. Also, we look at the protein sequences, that is nothing but the combinations of 20 amino acids. Then corresponding that also will be of different nature depending upon the organism and depending upon the what exactly the type of protein sequence we are looking at. Therefore, the text documents and protein sequences are some of the instances or examples of objects having variable length. The second object can be of molecular structure. We know that the molecular structure made up of complex 3D formulations, and that will be having different varied format, but all in 3D format, and that also is not of fixed size. The third can be the evolutionary tree, that is nothing but the tree like representation of the evolution of different species, and that evolutionary tree also could be able to be represented in tree format having variable tree size and tree length. All these instances are cases wherein which objects are of not having the same size, same length, same type. Then the question comes, how do we able to represent these type of objects having variable size, variable length and variable format? And that is where the kernels has its own significance, or kernels come to play. Assume that we have some way of measuring the similarity between objects, similar type of objects, suppose two text document. Can we have some sort of a similarity can be able to be drawn out of these two text document? Or if we have two molecular structure, can we have some relation or some similarity can be derived out of these two? And that is the concept we try to develop as far as the kernels is concerned. This type of similarity measure is possible. For example, if we consider the distance between two strings, looking at the corresponding distance, we could be able to have some sort of similarity between the two strings. With that background of objects are there without having fixed length, we could be able to introduce what a kernel function is. A kernel function is a real valued function from a set x to the set of real numbers of two arguments, such that k of x dash is greater than or equal to 0 and k of x dash is equal to k of x dash x, where x can be any abstract space. If you consider that set of all text documents, the x can be the set of all text document, or the x can be the set of all molecular structures, or the x can be the set of all evolutionary trees, etc. We take any two instances of that particular class and we define a function k such that k of x dash is greater than or equal to 0. That means the kernel function is non-negative, and k of x dash, that is the distance between, or that between x and x dash, will be same as say between x dash and x. In that sense, it is symmetric. Therefore, any function k from a class x to the set of real numbers having these two properties, that k of x dash is greater than or equal to 0 and k of x dash is equal to k of x dash x, such a function is said to be a kernel function. Any doubt about the kernel function, and why do we require the kernel function?
Represent the object in heterogeneous objects in
Exactly. That means if the objects which are of varying size or varying length that need to be represented, we require some format, and for that we require kernel function. Now we discuss on different examples of kernel functions. Having introduced what a kernel function is, we are looking at the most important examples of kernel functions. By now, we know what a kernel function is. A kernel function is a function from an abstract space x to the set of real numbers, such that k of x dash is greater than or equal to 0 and k of x dash is equal to k of x dash x. Some of the most prominent examples of kernel functions can be RBF kernels. The RBF stands for radial basis function kernels, radial basis functions. Kernels for comparing documents, Mercer kernels, linear kernels, Matern kernels, string kernels. These are some of the prominent examples of kernel functions. We will be discussing one by one in the next few minutes. First, we focus on RBF kernels, all the radial basis function kernels. Before dwelling directly into radial basis function kernels, we should have some idea about what is a radial basis function is. A radial basis function is nothing but a function which is evaluated at a point x with respect to taking some distance concept from a fixed point x. Here we have the examples for that. Suppose we consider r equal to 1. Suppose there is this x is equal to 0 and we take any point, suppose this is x, then the radial basis functional value of x is nothing but the distance of that x from some fixed point. Suppose we take the fixed point to be 0. Instead of 0, we could be able to take some fixed point, suppose c equal to say 0.5. Then the radial basis function of x, f of x, is equal to the distance from the point x to the point 0.05. Similarly, the radial basis function in this case is of the functional value of the point x is the distance of the point x from a pre-assigned fixed value. That value can be 0, any other fixed point. This is the case with when r is equal to 1. Suppose we consider r equal to 2, and suppose here we have one point, we call it as x. Obviously, it will be having two coordinates, x1 and x2. And suppose we, the easiest thing, suppose we fix the fixed point as 0, 0. Then what is the distance of this point x from 0, 0? That is nothing but square root of x1 minus 0 the whole square plus x2 minus 0 the whole square. That is the easiest one. Instead of 0, 0, obviously we could be able to have some fixed point. Suppose we fix point, we take it as a 1, 1, c equal to 1, 1. Take an arbitrary point x equal to x1, x2. Then we find the distance x minus c is nothing but square root of x1 minus 1 square plus x2 minus 1 square. Obviously, this could be able to be extended for any n, r3, r4, r5, etc. Therefore, anything which involves the concept of distance or norm, then that function is said to be a radial basis function. Okay, any doubt on what is the radial basis function? Therefore, as we have considered here, we have a radial basis function. It is a real valued function whose value at x is based on the distance of x from some fixed value c, and c is said to be the center. And some examples: f of x, norm x minus 2, the center we have taken c to be 2, and norm x where c is assumed to be 0, and this is the typical case of R1. This could be able to be extended for any other dimension. Also, in general, instead of the Euclidean space, we could be able to consider any space. Suppose considering having a kernel radius basis function, we could be able to introduce the radial basis function kernel. Suppose we take any two variables x and x dash, then the radial basis function based on these arguments x and x dash given by k of x, x dash is equal to e raised to minus norm x minus x dash square divided by 2 sigma square. We know what is norm of x minus x dash just by introduced. Then having that distance divided by 2 sigma square, where sigma square is nothing but the variance of the distribution from where the arguments x and x dash have been taken. When we have one space, abstract space X, whatever may be the space. The space can be the set of all text documents. The space can be the set of all molecular structures. The space can be the set of all evolutionary trees. Then we take any two instances or any two elements belonging to that particular class. We call it as X and X dash. Then having chosen two entities or instances X and X dash, we could be able to find the distance between them using the radial basis function. We could be able to apply that. Then correspondingly we could be able to have the kernel defined over this for using this formula. K of x x dash is equal to e raised to minus norm x minus x dash square divided by 2 sigma square, where sigma square is the variance of the distribution from where the arguments x and x dash have been taken. And this parameter sigma is said to be the bandwidth of the radial basis function kernels. Therefore, that is the RBF kernel. Any doubt on RBF kernel?
So for the two populations, we are saying that they have homogeneous variables.
That it is assumed that x and x star belong to the same space. Yes, it is assumed. We cannot compare. There was no concept of distance could be able to be established if the entities belong to entirely two different data sets. We move on to the next one, kernels for comparing documents. Suppose we have two documents, we denote these documents by xi and xi dash. We could be able to introduce the concept of distance in this using what is called the bag of words. What is the bag of words? Suppose we have the document say I, suppose the word J, and there is a document I. How many times the word J appearing in the document I, we count that, and that count is said to be the Xij, word count. Therefore, Xij denotes the number of times the word J occurs or appears in the document I. Here we can have a simple example. Suppose we have the first document, first sentence as today is Saturday. That is the first document sentence. Suppose the second, today is a holiday. Assume that today is not a holiday, okay? We are working today. Today is a holiday. Third, holiday is a nice day. I think all of us will appreciate holidays, right? Okay. Then what is the bag of words is, we leave out the what is called stop words appearing in the sentences. We focus on the genuine words appearing in that. Then for easy purpose, we assume that is a stop word, is a stop word, a is a stop word, is a stop word, a. All these unwanted words we remove. Then list out what are the other words appearing. For example, the words can be today, Saturday, then holiday, nice day. Suppose these are the words appearing in these sentences. Now, how many documents we have? Suppose this the first sentence is a document, first document, document number 1. Whether today is appearing in the document how many times? One time. Saturday, one day. Holiday, 0 times. Nice, 0. Day, 0. Similarly, for the second, we could be able to fit today, 1. Saturday, no. Holiday, 1. 0, 0. Then the third sentence, today, no, 0. Saturday, 0. Holiday, 1. Nice, 1. Day, 1. And this way of arranging, therefore we have taken the bag of words and we try to represent in a matrix format by taking this way the words along the columns and the corresponding documents in a row by column format, words and sentences, and correspondingly we could be able to represent in a matrix format. And from this matrix we could be able to get the count of each. Here it is 1, here it is 0, here it is 1, etc. We could be able to find the count of each of the words in the bag of words in each of the sentence. And that is what we will be using in our definition for comparing documents. I hope you understood what is the bag of words and how we will be able to represent two documents and the corresponding words appearing in a bag of words format, and which will help us to create the corresponding matrices. Any doubt? Okay, fine. Now we go back. That means here we have two documents xi and xi dash. Then xij denotes the number of times the word j occurs in the document. From the examples we have seen, yes, we could be able to find this xij values. That means the number of or the count of the number of times the word j occurs in the document I. Then here we introduce two different terminologies, term frequency and IDF. Term frequency, TF, and IDF stands for inverse document frequency. Then having this xij, remember xij is nothing but the number of times the word j occurs in the statement I. Take that plus 1, take the logarithm of that, and that will be denoted by term frequency, TF. Term frequency of xij is nothing but logarithm of 1 plus that count. Remember, by taking the logarithm, the bigger values could be able to be shortened without losing the corresponding value of that. That means we have TF, we have a document, we have the corresponding words. Xij denotes the number of times the word j occurs in the document I. That value is xij. Add 1 to that, take the logarithm of that, and we call that as the term frequency of that count. Now, we know that xij, already we have seen in the example that some of the words will be having the count 0. Remember in the last example, today is Saturday, Saturday is a holiday, holiday is a nice day. In the example we have seen that some of the counts are zeros, and there are words having the count non-zero value. The count cannot be less than 0, it can either be 0 or a positive value. Then we focus on the words having the count greater than 0. Then instance of that, how many are there, and take the sum of all that value, take the 1, and n is the total number of documents we are considering. Therefore, n divided by 1 plus sigma I equal to 1 to n, then incidence of xij greater than 0, how many such words are there? Then we call this as inverse document frequency. Why it is said to be inverse? Because we are taking 1 divided by this and multiplied by the total number of documents n. Therefore, from the xij, which is nothing but the number of times the word j occurs in the document I, we could be able to construct two additional things. First is the term frequency Tf of xij, and second IDF, that is nothing but the inverse document frequency of xij using this formula. Now, having these two things which could be able to be derived out of xij, we take the product of this Tf of xij into IDF of j, from j is equal to 1 to v for each and every words. Then that is said to be the Tf IDF of xi. Now, if phi of x, we call it as this Tf IDF of this one, this value we call it as phi of x. Then corresponding to x, we can have phi of x, which is nothing but Tf IDF of xij, and corresponding to the another argument x dash, we can have phi of x dash is equal to Tf IDF of xij dash. That means we could be able to have phi x corresponding to x and phi of x dash corresponding to x dash. Then the kernel on the arguments xi and xi dash, so suppose it's xi and xi dash is denoted by the dot product of phi of xi and phi of xi dash divided by the norm, square root of the norm, phi of xi, phi of xi dash. And this obviously a real number. Remember, the kernel function is a real valued function. This is a dot product, it's a real valued function. This is a norm distance, real value. This is norm distance, real value. Therefore, effectively right hand side we are getting a real valued function, and this is always will be greater than 0, and correspondingly, it will be obviously we will be able to get the values, basic properties of kernel function could be able to be satisfied, and this kernel function could be able to be used for comparing documents. Thus, when we have two documents provided, we could be able to list out the words by removing the stopping words. We could be able to find that list, which we call it as the bag of words. Using the bag of words and a number of documents, we could be able to construct the corresponding matrix, and using the each and every word and the occurrence of that word in the document, we could be able to have xij, that is the number of times the word j occurs in I. Using that, we could be able to calculate Tf, term frequency. Using xij, we could be able to have inverse document frequency. We take the product of this, it is Tf IDF or term frequency inverse document of that xi, and we define phi of xi as that value. Similarly, for the other argument x dash, we can have phi of x dash value. Take kernel function of xi and xi dash as the dot product divided by corresponding norm, and that is nothing but the kernel which is usually used for comparing documents. Okay, any doubt? Okay, any doubt, online students? Okay, fine, thank you, 32. Okay, thank you, 42. Okay, shall we move ahead? Okay, thank you, 44. Okay, we are moving ahead. Okay. We come to the next kernel, which is said to be the Mercer kernel. Suppose there are n input value. Let we call it as x1, x2, etc. xn. Then from these n inputs, we could be able to construct the kernel. Kernel can be anything, whether RBF kernel or typical any type of kernel. Then having that kernel, we could be able to have the kernel functional value for each pair x1, 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 x2, etc. x1, xn. Therefore, kernel function value for each pair of xi's which are there in the input set. And correspondingly, we create a matrix, that is kernel of x1, x1, kernel of x1, x2, etc. kernel of x1, xn, kernel of x2, x1, kernel of x2, x2, etc. kernel of x2, xn, etc. The last row, kernel of xn, x1, etc. kernel of xn, xn. Remember, each kernel being a real valued function, here we are getting a matrix whose order will be n cross n. Number of rows will be equal to n, number of columns will be equal to n. Then such a matrix is said to be a gram matrix. Therefore, a gram matrix is nothing but a matrix of n by n order, where the entries in the matrix will be nothing but the kernel functional values of each and every pair. Then, having this particular n by n matrix, we look at some properties of real valued matrices. What is the property we are talking about is the concept called positive definite. What is the positive definite? Suppose M is the matrix or K is the matrix in this case, we call it as a M is the matrix in general. Then we choose any column matrix Z, take the transpose of that Z, multiply that by M, multiply that net product by Z. Then if that is greater than 0, then such a matrix M is said to be positive definite. If you have not understood, we will go back to see an example. Suppose we call M equal to one simple matrix, we take say 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have the matrix. Obviously, this is a 3 by 3 matrix.
This is the gram matrix.
This can be a gram. It can be. We are talking about the property of positive definite for any matrix.
Got that.
It may be a gram matrix. It may not be a gram matrix. For the time being, we don't focus on the gram matrix. We are talking about the property of positive definite for this. Suppose we are considering a column matrix. And obviously, the transpose of that will be, transpose of a matrix is nothing but the matrix obtained by interchanging the rows and columns. Here, the number of rows can be suppose n, column matrix, number of column is equal to 1. Therefore, the transpose of that will be a matrix consisting of one row and n columns. For simple purpose, in order to illustrate this example, we take n is equal to 3. That means here Z we take to be a 3 by 1 matrix. For easy purpose, we take the entries of Z as 1, 1, 1, and n being 3, the transpose of Z will be a matrix of order 1 by 3. Obviously, the entries in the matrix will be 1, 1, 1. Now we consider Z transpose into M, that is equal to 1, 1, 1. This is 1 by 3. M, that is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. The order of M is 3 by 3. Number of columns of this matrix is 3. Number of rows of this matrix is 3. They are compatible for matrix multiplication, and we could be able to multiply and we will get a matrix. And what will be the order of that matrix? This is 1 by 3. This is 1 by 3. Sorry, 3 by 3. Therefore, we will be getting 1 by 3 matrix we will be getting. That means 1 by 3. If you want to, exact value is 1 into 1 plus 1 into 4 plus 1 into 7. That means 1 plus 4 plus 7. 5, that is 12. Next is 1 into 2, 2 plus 5, 7 plus 8, 15. Then 3 plus 6 plus 9, 3 plus 6, 18. And what is the matrix on the right hand side? That is nothing but Z transpose into M. Now, what we do is that whatever we have Z transpose into M, we multiplied that by Z. That means the matrix, that is nothing but, 1, 12, 15. This matrix is multiplied by the Z matrix. What is the Z? 1, 1, 1. That means 1, 1, 1. The value will be equal to, remember, this is 1 by 3 matrix. This is 3 by 1 matrix. The number of columns of the first matrix is equal to number of rows of the second matrix. Therefore, it is compatible for matrix multiplication. On multiplying, we get 1 plus 12, 13 plus 15, that is 28. Right? Sorry.
12 plus 50 plus 18.
Okay. Sorry, there is a mistake. Acha, this value, sorry, this is a mistake. This is 12, 15, 18. Sorry. And correspondingly, we get 12 plus 15 plus 18. That is 12 plus 15, 27. 27 plus 18, 45. This is greater than 0. Right? Therefore, in general, suppose M be any n by n matrix and Z be any column matrix. Column matrix is 1 by n, sorry, one column and n, sorry, it is mistake. M, n by n, column matrix, the order would be then Z transpose one by n. Whether we multiply these two first or these two first is immaterial, because the matrix multiplication is associative. Therefore, whether we multiply M with Z, then Z transpose with that, or first we multiply Z transpose into M, then by Z is immaterial, and if this will be, or if it is greater than 0, then the matrix M is said to be positive definite. Got the idea of positive definite? Therefore, for any given matrix of real valued values, we could be able to check whether that matrix is positive definite or not. Now, we come back to gram matrix. We know the gram matrix is a matrix obtained by forming a matrix using pairs of kernel values with respect to each and every element in the input set. Since this each and every kernel being a real valued function, we could be able to get an n by n matrix. Therefore, K is an n by n matrix. We could be able to check whether this K, that is the gram matrix, is positive definite or not by correspondingly taking one column vector, column matrix Z, and multiplying such a way the Z transpose into K into Z is greater than 0 or not. And assume that this gram matrix is positive definite, then such a kernel is said to be, then this kernel K is said to be Mercer kernel. Are you getting? Therefore, a kernel K is said to be a Mercer kernel if the gram matrix obtained by taking all kernel values of any two pairs of elements in the input set is positive definite. Such a kernel is said to be Mercer kernel. Is that clear? We have a set of input values x1, x2, etc., xn. We use some kernel. Using that kernel K, we find the kernel function values for each and every pair of elements x1, x2, etc., xn. Then we form the corresponding gram matrix, which will be an n by n matrix using some column matrix Z. We could be able to check whether Z transpose into this gram matrix K into Z is greater than 0 or not. That means we could be able to check whether the gram matrix is positive definite or not. If the gram matrix is positive definite, then the original kernel K is said to be a Mercer kernel. Is it clear? Any doubt? Online students, any doubt? Mercer kernel, positive definite matrix? Okay. Okay, thank you. 32, 42, 44, 43. We move ahead. Then we come to the linear kernels. Suppose x and x dash be any two arguments, then we take x transpose into x dash, that is the dot product, then that value is said to be the linear kernel. It is very simple. X transpose into x dash, the dot product of that two arguments, and that is said to be the linear kernel. Then we come to the next, which is said to be the Matern kernel. The Matern kernel is defined as K of R using this formula, where R is nothing but norm of x minus x dash, and this notations V greater than 0 and L also greater than 0. And if V is equal to 1 upon 2, this could be able to be reduced in a much simpler formula given by e raised to R by L. Then any kernel given using this formula is said to be a Matern kernel. Okay, we move ahead. We come to the next type of kernel, which is string kernel. Suppose we consider two strings. Many times we need to have some sort of a similarity between strings, especially in the field of bioinformatics. When we want to have two DNA sequences, or we have two protein sequences, and we wanted to know how similar they are, and we need to have some sort of a measure in order to compare that and some similarity to be created. Here we consider two protein sequences, amino acid sequence formed out of any 20 amino acids. We could be able to have a number of sequence of alphabets out of 20 alphabets. The first one is a protein primary sequence. Similarly, second one is also a protein primary sequence. 2 amino acid sequences we have. And many times, not exactly the full sequence, some sub part of the sequence, if they are appearing it, that will be having great impact in the field of bioinformatics or molecular biology. That means we wanted to know the occurrence of some substrings in two sequences, and we wanted to know how they are repeated and the corresponding nature. For the simple illustration, after having these two amino acid sequences, we look at a substring called LQE and check it whether LQE is repeated in these two strings or not. On a casual look, if you go through the first amino acid sequence, we could be able to notice that at least one time LQE is repeated. Similarly, if we go through the second amino acid sequence, we could be able to notice that at least 2 times LQE is repeated. Therefore, the substring LQE is repeated in this. Then we define the number of times the substring LQE is repeated in the string number 1 or the string number 2. Suppose S we denote as the substring, in this case LQE is the substring, and the string, suppose the first is the string x1, that is this string, then the number of times the substring LQE instead of S over here appears in the string number 1 is nothing but 1 from the document. Similarly, the number of times the substring LQE repeated in the string 2 is 2. Then that count we call it as phi s of x. Therefore, phi s of x is nothing but the number of times the substring s repeated in the string x. Therefore, when we have two strings x and x dash, we could be able to count the number of times the substring s repeated in the substring that is given to be phi s of x. Also, for the substring x dash, we can count the number of times the substring S repeated in the string given by X dash. In this illustration, if S is LQE and X being the first string, X dash being the second string, phi S of X will be equal to 1 and phi S of X dash will be equal to 2. Then we can have a number, some value W of S, which usually chosen by the programmer, usually depending upon lies in between 0 and 1, and correspondingly for each and every string, substring we want to check it, and we could be able to have the summation of that value, and that summation is said to be the kernel of X and X dash.
So my question was regarding the equation that sum of Ws of phi Sx and phi X dash, where Ws is it looks like a weight, like that would be assigned for every string.
Yes.
And that would be determined by the importance of each string, or it is subjective to the...
Okay, it is a very good question. Basically, assume that in a hypothetical situation, some of our relative is infected with a disease. It is similar to a known disease. For the known disease, there is a proper medication available. But this particular disease being unknown but similar to that, and also assume that there is no medication for this unknown new disease. A pharmaceutical company wants to formulate or develop a new drug for this. We know the pattern of the disease by having the chunk of substring in the DNA sequence or protein sequence, etc. And we also know that the similar disease drug, what is the corresponding formulation. Therefore, considering that this particular disease having non-biological feature of could be able to be taken as nothing but a substring, and some of the part will be having much more impact than the other parts, we could be able to give more weightage to that part than other unimportant parts. Therefore, when the pharmaceutical company wants to develop a new drug, they could be able to address this issue, and correspondingly we could be able to formulate that. Therefore, it depends upon what is the problem we are facing it and what exactly we are looking for it, and correspondingly we could be able to decide. Obviously, not just the programmer or the coder, but obviously the domain experts' help might be needed, because only domain expert could be able to understand it, what exactly the significance of that substring is. Obviously, it is not part of the formulation of the kernel in abstract sense, but depending upon what is the domain we are focusing on and what exactly we are looking for out of that, and based on that we could be able to have the value for the W of S. Obviously, as the terminology shows, W of S, weight corresponding to the substring S, that varies, because remember S varies over A star. A star is nothing but the collection of substring with respect to that abstract space. Okay, any other doubt? Online students? Okay, here is the question. Matern kernel would be used for a type of data, linear kernel for another type of data. Is perfect. Yes. The type of kernel is used depending upon the type of data we have. All kernels may not be able to be applied on all type of problems, and depending upon the type of data we have, we could be able to use it. Okay, number 42. The second part of the question, does choosing a kernel depend on the data we are working with? Yes. Sometimes the problem at our hand could be able to be tackled by all types of kernels, and sometimes only one type of kernel. Remember, all kernels are not Mercer kernels. Therefore, if we require to have a Mercer kernel, only the kernel which satisfying that property only could be able to be used. Is that fine? 42. Okay, we move ahead. Thank you. That was the first part of the kernel. We introduced the kernel and we listed different kernel functions. Now we move to the next part, that is called using kernels inside GLMs. Some new terminologies may be popping up now. First, we introduce the idea of called exponential family. Having known different probability distributions, if you recall, some of the elementary probability distributions are Bernoulli distribution, binomial distribution, Poisson distribution, normal or Gaussian distribution, gamma distribution, beta distribution, T distribution. There are a number. And if you just try to recollect the corresponding probability mass function corresponding to discrete distribution and probability density function with respect to continuous distribution, there are distributions whose PMF or probability mass function or PDF probability density function have a component exponential e raised to. For example, Poisson e raised to minus lambda into lambda raised to x divided by x factorial. Binomial NCX p raised to x q raised to n minus x. Gaussian 1 upon square root of 2 pi sigma e raised to minus x minus mu the whole square divided by 2 sigma square. All these PMF or PDFs will have some exponential component as part of that. Any distribution whose PMF or PDF has some exponential component as part of it, then that distribution is said to belong to exponential family. Is that clear? A distribution is said to be in an exponential family if its PMF or PDF consists of some exponential component. There can be a number of examples, Bernoulli, binomial, Poisson, Gaussian, all these are examples of. Obviously, there are distributions which do not have PMF or PDF component, doesn't have any exponential, that will not be part of exponential family. Therefore, we have distributions which are belong to exponential family. The first terminology we should be familiar with this is that exponential family. Is that clear? What is an exponential family? Exponential family is a statistical distribution whose PMF or PDF has some exponential component. Fine. Then we move to the next one, generalized linear models, or we call it as a short form GLMs, generalized linear model. Generalized linear models are any statistical or machine learning models whose output density is in the exponential family. That means when we substitute P of x is equal to, we need to have some exponential component part of that. Obviously, that will come whenever the PDF or PMF have exponential, automatically the output density will be having the exponential family. Second, the mean parameters are a linear combination of the inputs passed through a possibly a non-linear function. Suppose x1, x2, x3, etc., xn are the values. If we take say w1 x1 plus w2 x2 plus etc. plus wn x, this is nothing but the linear sum, linear combination of the inputs. Then if the mean parameters, that means parameter of that will be the linear combination of the inputs passing through possibly a non-linear function, then if these two functions are if these two properties are satisfied, then such a model is said to be a generalized linear model. An example for a generalized linear model for any machine learning student would be, first will be logistic regression. Remember, because the formula for the logistic regression is e raised to some sum divided by 1 plus e raised to sum. E is there, belong to exponential family. Then second, e raised to sum, that means the corresponding mean parameters has the linear combination and going through some nonlinear function. What is the function we used? Sigmoid function. Therefore, the logistical regression is a typical example for a generalized linear model. Then, that is two things we are familiar: exponential family and generalized linear model. Then we come to what is called the kernel machine. A generalized linear model, that means two things are satisfied: output density is in the exponential family and the mean parameter is nothing but linear combination passing through some non-linear function. Therefore, such model, that means a general linear model, where the input feature vector has the form phi of x is equal to k. What is k? Our kernel function. Kernel of x mu1, kernel of x mu2, etc., kernel of x mu k, where mu k are the centroids of that subparts. Therefore, we have a set of observations and we could be able to have centroid for some subparts. Suppose mu1, mu2, etc., mu k being the corresponding parameter representing that subparts, we could be able to calculate k of x mu1. Remember, already we have kernel function. K can be any of the kernel function which we have seen earlier. K x mu1, k x mu2, etc., k x mu k. Then if the input feature vector will be having this k component, each of the component is a kernel function value of some input and the corresponding centroid, then such a model is said to be a kernel machine. That means what is the significance of this is that, remember, we are inside. K is where? K is inside. Inside where? Phi of x is the input vector. Therefore, this will be given to as input, where each input vector consisting of k component, and each component is formed out of kernel function, and that also having the generalized linear model characteristics, then such a thing is said to be a kernel machine. That means we could be able to keep kernel inside for subsequent activities. Then if k is an RBF kernel, remember, kernel in this example in this formulation can be anything. If that k is a RBF kernel, remember what is RBF kernel? Yes, distance, norm concept is there, distance. Therefore, if k is an RBF kernel, then such a kernel machine is said to be a RBF network, radial basing function network. If you recall, Those who are familiar with the neural network could be able to radial basis function network. Remember, there the activation functions are radial basis functions. The norm concept is there. Therefore, all these are interconnected. Therefore, roughly a kernel is nothing but, let us leave out the technicalities. What is a kernel? Kernel which transforms something, which changes something. Kernel of x and x dash. Bringing x and x dash, it brings something new, a numerical real value. Therefore, kernel is nothing but which transforms into a real value.
It is very similar to a definition of a random variable, where also a random variable is a, which maps set of observations to real line.
Yes. Okay. Any other doubts? Any other doubts? That means here we just introduce the next sub module of the kernel, that is using kernels inside GLMs. Few things we introduce for the first time: the exponential family, generalized linear model, the kernel machine, and the kernel in that kernel machine can be any kernel, and if we fix that kernel to be an RBF kernel, then such a network is said to be radial basis function network. Okay, here is a doubt. Shouldn't it be k x1 mu1 x2 mu2? Let us come back. Yeah, this can be anything. X stands for a some, a parameter or something, therefore it can be anything, no issues. Okay, 42, this F can be anything, fine. Second, 42, for the input feature vector, a kernel machine, yes. Okay, we move ahead. Can we move ahead? Okay, thank you. Then we come to the next part, that is called kernel trick. The trick is the word, what it conveys. Trick is not something formal, am I right? Trick is we try to some way manipulate to make things simpler. The kernel trick is the trick we play on kernels in order to make this is much more effective. For that we consider this data. Here we have a collection of data. It is very nicely, clearly, cleanly demarcated using a line, something like this. There is no overlapping of this brown dots and this green dots. Therefore, it is what is called linearly separable data set. A data set is said to be linearly separable if one part of the data could be able to be segregated from the other using a linear line or a plane, etc. Therefore, it is a two-class linear separable data sets. If the data is such a very clean, neat and placed such a way that there is a difference, there is a distance between the data belong to one set and the data belong to another, we could be able to have some decision boundary like this, linear boundary like this. Therefore, here we have a linear decision boundary, that means here is a straight line here we have, which could be able to separate. In fact, not one straight line, we can have infinitely many straight lines which are in between these dotted lines. Any such line can be a linear decision boundary. Here is the difference in the data. One of the main feature of this data is that it is not linearly separable. If we compare with the previous one. This is very clear to us that we could be able to have a number of straight lines to separate the data, and in this case it does not feel, and if you try we will be able to get the linear line like this. Obviously we fail to separate the linear decision boundary, fails to separate the non-linear data. We cannot have a linear separation for separating the non-linear data set. Then how do we do? Suppose we want to classify all the elements over here together and all the elements over here. What do we do? That is our concern. Then looking at this data, instead of looking the data plotted on a two-dimensional framework, assume that it could be able to be plotted on a higher dimensional framework. Here we have x and y axis. It is the scattered diagram we have drawn on the two-dimensional xy plane. Instead of that, we assume that the data could be able to be represented in a higher dimensional structure. It is something like this. Every point has two components, say x and y. We transform this non-linear data which is in R2 to a framework in R3 using the transformation phi of xy equal to x, y, x square plus y square. Therefore, phi is a function from R2 to R3 using the functional representation phi of xy equal to x, y, x square plus y square. Each and every point has two components, x and y. Since x and y are there, we could be able to calculate x square, we could be able to calculate y square, we can add it up. That means for every xy, we could be able to have additional component x square plus y square, and correspondingly we could be able to have x, y and z coordinate for every element in the original figure. Therefore, this picture could be able to be transformed to this picture using this transformation given by phi of xy equal to x, y, x square plus y square. Are you convinced about it? Are you convinced about it? Yes. If that being the case, you must have noticed there is a clear demarcation between the colors of the elements plotted here. All the blue ones over here and the non-blues on top. That means we could be able to have a plane drawn to separate these blue dots and these colored dots. That means in this process we have converted the data to be linearly separable. Therefore, if you go back, originally we have this data which is not linearly separable. We try to transform this data elements using a transformation or using a function phi given by phi from R2 to R3 given by phi of xy equal to x, y, x square plus y square, and correspondingly we could be able to have a diagram picture in the 3 dimension, and the nature of this scattered diagram is such a way that the data points could be linearly separable. And what is the beauty of this is that suppose here we have the 3-dimensional representation. Suppose we project this into 2 dimension. What is x square? Remember, what is the function we use? X square plus y square. What is x square plus y square is equal to something? Signifies circle, right? Therefore, we could be able to, when we project this into a two-dimensional one, we could be able to have a circular separation of the data points, which was impossible to even imagine in the case of a linear separability, because linear separability demands that the data points to be separated using a line. Therefore, this way we could be able to have separation in the linear fashion in a higher dimension, as well as non-linear separation in the original dimension. And this is said to be kernel trick. Therefore, this is the trick we played on the data set. It is said to be kernel. Why it is said to be a kernel? Phi of xy. Remember, what was the transformation function? Phi of xy. X, y, x square plus y square. Therefore, this kernel trick is the process used to convert a non-linear data to a higher dimension to make it linearly separable. Okay, any doubt? We have just introduced the concept of kernel trick. Therefore, kernel trick is the mechanism, is the process we use to convert a non-linear data to a higher dimensional one in order to make it linearly separable. Any doubt? Online students, any doubt? 42, whether the audio is clear now? Okay. Number 5, thank you. Any doubts? Online students, any doubt? Okay, thank you. Number 5, we move ahead. Now we come to the next topic, that is support vector machine. Suppose we have a data consisting of two types. One is represented by dash circled by these red lines, red circles. Another type given by this plus sign circled by black shade. We wanted to separate or to classify these two different types. We could be able to have a linear line, straight line like this. In fact, we can have infinite number of lines drawn over here. Then, if you look at this side, this is beyond this we cannot have any line. Similarly, beyond this we cannot have any line. Therefore, these two lines, these dotted lines, shows the margin, and any line drawn between these margins will be able to act as a linear separation. Then this distance between these two margins, these two lines, is said to be the margin of that. Then the function of the support vector machine is to have this type of line in an R2 or higher dimensional plane in the case of higher dimensional problems. We wanted to have a linear higher dimensional plane to segregate the data points into two classes. Then what are the inputs? We suppose we call it as, we denote X as the input set and Y as the output set, and suppose for easy purpose we assume that y consists of only two things, either belong to class 0 or class belonging to class 1, 0 or 1. It is a binary separation. Then training set consists of the input values and the output value, and yi, it shows that whether it belongs to the 0th class or it belongs to the class represented by 1. Therefore, we want the classifier means we have a function which depends upon the input value and the parameters specific to that classifier. It can be anything. Then we are formulating, creating a model using f of x w b, b is the base and w is the corresponding weights, and using sign of w into x plus b. And in this formulation we have a separating line. We wanted to check whether there is a training error involved over there or not. This is also said to be what is called empirical risk or the training error. The empirical risk is given by R empirical of alpha, alpha being the parameter in this case, equal to 1 upon m into sigma I equal to 1 to L m, L of f of xi alpha yi. That means L is the loss function. Assume that we take the loss function as 0, 1 loss function. That means we know that one input is given, corresponding output is either 0 or 1, and the output is matching with the expected output. We say that it is exactly matching, that is value will be equal to 0, otherwise it is 1. That way we could be able to put it. That means L is 0, 1 loss function. There is no error or there is an error. We could be able to calculate using that. Therefore, this is said to be the empirical risk. M is nothing but the total number of elements in the training set. Then the training error, suppose we train the model and correspondingly we come to a model which minimizes the empirical error or training error, then we put that into the actual test case. Then the training error may not be the same as the testing error. Then the overall risk or the testing error is given by the formula R of f, f is R of alpha, where alpha is the parameter, integral L of f of x alpha y into d into p of xy, where p of xy is said to be the joint distribution function of x and y, which is unknown because we do not know which is the actual function which would be able to give the full 0 error, and d is the one we are not familiar with this, and we will be using that in the subsequent slides. For the time being, we just introduce how we will be able to formulate input output, training set, classifier, designing the model, finding the empirical error and finding the overall error. This assumes that certain things, here what we left, what is nothing but the d, and we are introducing that d which is said to be what is called VC dimension, because the concept of support vector machine and the corresponding theory have been provided by Vapnik and Chervoninskis, and they formulated the concept of what is called VC dimension. V stands for Vapnik and C stands for Chervoninskis. Consider this figure. In this case, what we have is R2. We have 3 points. Then suppose we have a line to separate the points. One way the line can be drawn like this, so that this shaded portion such a way that 2 points are over this side and 1 point is the other side. This is exactly the counterpart of this separation. That means having this is selected and this is separated. This is selected, this is separated. This is selected, this is separated. Then Can we, suppose we fix this data points to be 3 in R2, can we have any other ways of having this separation? Can we just visualize any other form? Yes, we can have something like this. Is that fine? We have the separation of this and the counterpart of this. Do we have any other separation? Do we have any other separation? Yes? Yes. We can have something like this. Is the final separation, or can we have anything more? Something like this, if you want to have, it is not separation, but it is, if it is mandatory to have the line in that square, we can have something like this. And beyond this, can we have any other ways of separating it? Okay. Assume that instead of these 3 points, suppose we have 4 points in that square. Is it feasible, is it possible to separate 2 similar type away from another 2 dissimilar type? This is what we are asking. If we have this type of data points, we can separate like this, we can separate like this, we can separate like this. But if we have 2 types like this, can we have one line to separate these 2? No. That means if we have 4 points, we cannot separate using one line. Instead of 4, we started with 3. Instead of 4, if we have only 2 points, can we separate using a line? Yes, we can separate. Instead of 2, if we have only 1 point, can we separate? In the square, we have only 1 point and 1 line. Can we say that, can we take 1 line, point on one side, no points on the other side? Yes. Therefore, we look at the different scenarios. Only 1 point, 1 line can separate. Having 2 points, 1 line can separate. Having 3 points, 1 line can separate. Having 4 points, no. Having 5 points, if 4 cannot be separated, how 5 cannot be separated? 6? No. 7? No. 8? No. No other number cannot be separated by a line. Therefore, the maximum number of points in R2 can be separated by a line is 3, and that is said to be VC dimension. The VC dimension is the maximum number of points that can be separated in all possible ways by a set of functions. Remember, the line can be of anything formed by y equal to mx plus p of any value of m and c. Therefore, that can be a function, and correspondingly we could be able to have this type of maximum number. Therefore, VC dimension is the maximum number of points that can be separated in all possible ways by that set of functions. As we have noticed in the case of R2, the maximum number of points that can be separated by a line is 2. We can go on checking. If instead of R2, if we have 3, we could be able to show that 4 points could be able to be separated maximally. For in general, if the Rn is the surface and hyperplanes in Rn, the maximum number of points could be able to be separated by that hyperplane is n plus 1. Therefore, the VC dimension for any hyperplanes in Rn would be equal to n plus 1. Any doubt? VC dimension, any doubt? Online students, any doubt on VC dimension? Okay, thank you. Number 5. Can we move ahead? Okay. Now we got the idea of VC dimension. VC dimension is the maximum number of points that can be separated in all possible ways by a set of functions. And for Rn, the VC dimension for hyperplane is proved to be n plus 1. Then the question, what is the significance of this VC dimension? And we have noticed earlier that there is an empirical risk and the true risk. Empirical risk is nothing but the training error, and the true risk is nothing but the test error. We formulate a model based on the data sets we have, and whatever the error we are getting, that is the training error or the empirical error. But in the actual scenario, we put that model into practice, and based on the actual data sets, then when the model is active, then that will be showing some error, and that error is said to be the true risk or the test error. And there has been one formula which gives the upper bound for the true risk based on the empirical risk. Whatever the model we have created and what is the maximum error that can be observed when it is put into practice, and there is an upper bound, and that is given by R of alpha, that is a true risk will be less than or equal to R EMP, that is empirical error of the model with parameter alpha, plus square root of h into log of 2m by h plus 1 minus log of eta by 4 divided by m, where h, this h is nothing but the VC dimension. Remember, in the case of support vector machine, the objective is to find a hyperplane to segregate data values. Then that hyperplane, how many data points maximally separate, that value is given by VC dimension. That means whatever the hyperplane we formulated, with respect to the hyperplane, we know the value of h, VC dimension, and m is nothing but the number of elements in the training set that we know, and eta is the value we assign eta equals 0.05 or etc. What is the error within which we want to have this to be done, pre-assigned value, and based on that we could be able to calculate an upper error for the empirical risk. Therefore, based on the training error and based on the VC dimension of the hyperplane we formulated or decided or developed to separate data values, and the number of elements used in the training set, and for a pre-assigned positive value eta, we could be able to have an upper bound. This true risk value can never go beyond this. That means we could be able to have some sort of a insurance cover for our model. Test error cannot go beyond that. We could be able to have some sort of a pre-assigned value, we could be able to have some sort of a definiteness with respect to that model. That is the significance of VC dimension. This could be able to have, remember all things are formulated using training data. Remember REMB of alpha, based on the training data we could be able to have the test error. Based on the training data we have the value of m, that is the number of elements in the data set, and only eta is we decide, we provide, and all else are part of the training. What additional we want? Only the VC dimension, that is provided by the model or the hyperplane we formulated or we developed, and that is the significance of VC dimension. Okay, any doubt about?
So that h is multiplied by only the log or the whole?
This is only by this.
Okay, the first term.
Yes. Okay. Online students, any doubt? Okay, thank you 42. Thank you 5. Okay, thank you 11. Okay, we move ahead. Now, we just revise what we have done today. We started with the kernels. We introduced what is a kernel function is. What is the significance of kernel function? Kernels are required, or kernel functions are required because there are objects which do not have fixed size or fixed length. We cannot have a fixed length feature set. There can be different examples for objects which do not have fixed size or fixed length. They can be text documents, protein sequences corresponding to variable length, or molecular structure having complex 3D structure, or evolutionary tree of variable size and shape. These objects also need to be represented in order to be used for machine learning modeling. For that, we introduced kernel functions. In a very non-technical sense, kernels are nothing but something which transforms. Therefore, a kernel function can be defined as a function k from the set x to the set of real numbers r, such that k of x dash is greater than or equal to 0, non-negative, and k of x dash is equal to k of x dash x, symmetric, where x is any abstract space. Then we considered the different kernel functions. The different kernel functions we have seen are RBF kernel, radial basis function kernel. For that, we introduce RBF function, a function which uses the concept of distance. Then we have seen the kernels for comparing documents. We introduce idea of bag of words, Xij, which represents the number of or the count of the word j occurring in the document I. Based on that, we introduce the corresponding kernel. Then Mercer kernel. For that, based on the value of kernel, we formulated a matrix. The matrix is said to be the gram matrix. The gram matrix is nothing but a matrix of kernel values of any two pairs of arguments from the input set. And we introduced the idea of positive definite. The matrix K, an n by n matrix, is said to be positive definite if there exists a column matrix Z such that Z transpose into K into Z is greater than 0, and the kernel K is said to be a Mercer kernel if the gram matrix is positive definite. Then we introduce the linear kernels. The linear kernel is given by K of x dash is equal to x transpose into x dash. Then Matern kernel, little bigger formula which is used in order to represent the Matern kernel. And finally we have the string kernel in order to represent the outcome by using the repetition of a substring in two documents in those two strings, using the formula K of x dash is equal to sigma WFS into phi s of x into phi s of x dash, where phi s of x is nothing but the number of times the substring s appears in the string x. Later we introduce the kernels inside GLMs, that is generalized linear models. We introduce new concepts like exponential family, generalized linear models, kernel machines, and also we mentioned that if the kernel K is a RBF kernel, then such a machine is said to be radial basis function network. Then we introduce the idea of kernel trick. Kernel trick is nothing but the process or the tool which help us to convert data sets which are not linear separable. By converting the data set into higher dimension, we could be able to make that linearly separable. And we used a transformation. In the example, we used a transformation of phi of x is equal to x, y, x square plus y square. And we have noticed that by projecting that back to R2, we could be able to have a circle, and that means the data sets could be able to be non-linearly separable. Later, we introduce some additional features of support vector machines, the empirical risk and the overall risk, this being different. We have seen how we will be able to get an upper bound for the empirical risk or the test error. For that, we introduce the concept of VC dimension. VC dimension is the maximum number of points in Rn which could be able to be separated by a hyperplane. And we use that VC dimension in order to get an upper bound for the test error using the empirical error. I just want to say thank you to each one of you for having the patient listening. See you next day. Thank you.